Chapter 17, Section 2, Oxidation of Fatty Acids, Part 2. Remember, this was a long section, so instead of one 40-minute lecture, I've split it up into two 20-something minute ones. So, fatty acids are going to be transported, carnitine transport, into the mitochondria, where they're then going to be beta oxidized, having a coenzyme A attached to the carboxyl end, and then cut, add another CoA, cut, another CoA, cut. So you end up with two carbons attached to a coenzyme A, which for all intents and purposes is acetyl-CoA. Okay, there we go. Acetyl-CoA can feed directly into the citric acid cycle, where it's going to be consumed, releasing carbon dioxide, water, and you're going to get a whole bunch of ATP. We've seen this. This was pretty much everything Chapter 16 was talking about. So if you count it out, palmitoyl-CoA, which is 16 carbons, going to need 23 oxygens, 108 inorganic phosphates, 108 ADPs, going to yield coenzyme A, free CoAs, 108 ATP, 16 carbon dioxides, and 23 metabolic waters. So think about that. You start off with a fatty acid that's 16 carbons in length, and you're going to end with 108 ATPs. Not bad. Again, it's here's numbers where somebody sat there and calculated out the theoretical, and no, I'm not going to sit there and make you know this type of shit, because honestly, I don't always trust these numbers. I'm not saying they're wrong, but they have to make a few assumptions on the way. Just know, for me, it's, the FADH2s are going to contribute less energy from their electrons than NADHs, and that's only because FADH2 enters into the electron transport chain midpoint, where NADH enters into the electron transport chain and gives its electron up at the beginning of the transport chain. When you go through and you calculate, okay, so 1 palmitoyl, beta oxidation, acyl-CoA dehydrogenase, we see for that 1 palmitoyl, 7 FADHs, DH2s. The beta hydroxy-CoA dehydrogenase, 7 for every 1. Within the citric acid cycle, once things start, 8, 8, 8, and 8 here, 8 there, 8 there, 8 there, and so on. These numbers, yes, I trust. This is more the theoretical. You pump so many electrons across for every one excited electron entering in the transport chain. You pump so many hydrogens, and as the hydrogens flow back, the ATP synthase spins so many times, and for every time it's spinning, for X number of revolutions, this is how many ATPs will be made, blah, blah, blah. That's where I get a little. Enol-CoA hydratase. Cool. Love that. Enol-CoA hydratase has an issue. It only works with saturated fatty acids. What happens when you have an unsaturated fatty acid? That means you have a fatty acid that's got a carbon-carbon double bond. Well, gonna have to go through a few extra steps that we didn't talk about in part 1 of this section's lectures. You're gonna have to go and you have to convert that cis double bond back into a trans bond. Then you're gonna have to reduce it. Gonna have to take the cis, turn it into trans, and then get rid of the double bond. Here's what we're looking at. Okay, somewhere you have 18 carbons here. So this is ollyl-CoA. CoA is attached here at the terminal carbon with the carboxyl. So this is carbon 1. Somewhere within, you've got the carbon-carbon double bond. Here it's carbon 9, hence ollyl-CoA. You can go through carbon 1, carbon 2, cut, which is now this becomes carbon 1, that becomes the new carbon 2, cut, that becomes the new, that becomes the new, cut. And you can sit there and follow this pattern, exactly what we've talked about with part 1 of this section's lectures. Every time you cut, you add a new CoA to the terminal end, cut, add a new, cut, until you get here. This is now going to be carbon 1, carbon 2, and that will be carbon 3 at that time, as they're showing here. The problem is the enzymes that would go through and make, remember you got to do the whole add in a hydroxyl, turn it into a carbonyl, and do all that stuff, so that what is now carbon 3 has a carbonyl, so that when you cut between carbon 3 and carbon 2, carbon 3 now becomes the new carbon 1 with a carbonyl group that can now be attached to the incoming CoA. Well, can't do that with this double bond. So first you got to get rid of the double bond. So you go through, you cut, get rid of those acetyl-CoAs, normal beta oxidation. Now you're here with this carbon-carbon double bond. First, you got to make some changes. All right. Isomerase is going to take this carbon-carbon double bond, hydrogen up, hydrogen down, or both hydrogens up, and it's going to make it hydrogen up, hydrogen down. Still got a carbon-carbon bond there. This can be worked with, because remember, part of those steps of adding in the hydroxyl, turning it into the carbonyl, is you had to have a double bond there at some point. If you have a multiple, a polyunsaturated, so you have multiple carbon-carbon double bonds, well, you go through this, do the same thing again. Transform cis delta 3, cis delta 6. Same process, just more steps. If the double bonds are close, like they're showing here, cut, normal beta oxidation. But here, 2 alpha, 3 beta. Do the isomerase again. So it's now the double bond between, instead of being between 3 and 4, is now between 2 and 3. It's one of those steps we talked about before. And now once that's formed, you can go through, add the hydroxyl, turn it into a carbonyl here. You're good to go. And then you just do the same thing over here. Once this cuts there, this becomes the new 1, that becomes the new 2. You go through, change things around again, and you just keep doing that process as many times. So as we saw in the last slide, okay, you're going to have the carbon-carbon double bond between 2 and 3, 4 and 5. You're going to use 2,4-dienol-CoA. 2,4, that's where the carbon bond is, the double bond comes after, so that's out of the numberation, the dienol-CoA. Reductase, you're going to take NADPH, you're going to strip off that hydrogen, and then you're going to add it in. Boom. So now you're going 1, 2 double bond, 3, 4 double bond. Now you're going 1, 2, 3 double bond between 3 and 4 and 5. Isomerase switches that double bond up to between 2 and 3. Hence trans 2, delta 2. And now you can go through our normal steps of oxidation that we've seen part 1 of section 2. What happens if you get odd numbers? Okay, because everything we've been talking about here has been even numbers, 2 by 2 by 2 by 2, but not everything's even. Well, okay, not a problem. You cut 2 by 2 by 2 by 2 whether it's saturated or unsaturated. If it's unsaturated, you follow the steps we've covered in the previous 4 slides until you get down to the final 3. This is referred to as propionate. CH2, CH3, CH2, carboxyl. This happens quite often. 3 carbon compounds formed by cattle, other ruminant animals during carbohydrate fermentation. It's kind of interesting. So you get a fatty acid that gets cut, and you end up with a fermentation product. All right. Or something that resembles a fermentation product. Anyways, you go through, you end up with the final 3 carbons. The carboxyl here, you're going to replace one of those oxygens with CoA. So you've cut every 2, making acetyl-CoA until you get to the final 3, and now you have propionyl-CoA. Propionyl-CoA, 1, 2, 3, has the CoA, carbonyl, everything's normal there. You're going to add in a carbonate. Remember, you're going to use that biotin in the B12. Oh, I can't remember. I don't want to say B12, but that doesn't sound right. The coenzyme with the biotin molecule that's going to act as a holder, hold the propionyl in place, going to hold the carbonate in place so they can interact. And you're going to use energy from ATP so that now you can have 1, 2, 3, 4 carbons with the coenzyme A. This is known as D-methylmalonyl-CoA. Can't do much with D-methylmalonyl-CoA. So what can you do with the methylmalonyl-CoA? Well, we're going to swap some things. We're going to take this carbon that just came from the carbonate that has the carboxyl here, and we're going to swap it with this carbon, carbon 1. So we're going to swap them around. This carbon with the CoA is going to come up here to carbon 2. This carbon's now going to come down here and become carbon 1. This is a epimerase. Okay, it's making a stereoisomer of the original. And again, we're going to take this methylmalonyl-CoA, L-methylmalonyl-CoA, that we just moved the CoA and its carbon from the carbon 1 place to this now side chain. And we're going to utilize B12, coenzyme B12 with its biotin thing. And we're now going to swap the hydrogen for this group. Pop this one off. It's going to be held by the R groups, the biotin. This one's going to be removed. This is going to be added in right there, and then a hydrogen to fill in there. 5-deoxydenylyl cobalamin. Wow, that's a good name. Cobalamin. So it's not the biotin I said it was. That was the previous one. I don't know why I said biotin. Don't feel like talking. That D-methylmalonyl that we talked about, that's going to become the succinyl-CoA, mid-steps of citric acid cycle. So it could either become oxaloacetate all over again, or it can be reversed and rebuilt and become something else. Turns out this is an intermediate in fatty acid synthesis. So, the acetyl-CoA, malonyl-CoA can become fatty acids, start building those back up, 2 by 2 by 2 or whatever, 4 by 4 by 4, however many. Or it can go be transported in and utilized in fatty acid degradation to become acetyl-CoA all over again inside of the mitochondria and enter into the citric acid cycle. It's interesting. High blood glucose means your insulin's going to go up, meaning your phosphatase levels are going to go up. So this ACC that would normally take acetyl-CoA and turn it into a malonyl-CoA now becomes active. Cool. That works. Malonyl-CoA is going to be utilized to build up your fatty acid stores, start making them again. Malonyl-CoA levels going up, means your fatty acid, that whole carnitine transferase thing, taking any fatty acids and moving them into the mitochondria so they can be beta oxidized to form acetyl-CoA, that gets hindered, which makes sense. You're trying to build up fatty acids, and this whole side of the equation is trying to take fatty acids, move them into the mitochondria so that they can be broken down and utilized as energy. These two sides are at polar opposites. This side's trying to build up, this side's trying to break down. High blood glucose means you got enough glucose. You don't need any more energy from fatty acids, so you build up. Low blood glucose, glucagon kicking in. You're wanting to break down sugars and you need energy. Well, because fight or flight's about to kick in. Well, take whatever fatty acids you got. Don't store them. Put them into the mitochondria. Break them down. Get all the ATP you can, because all the glucose you have in the cytoplasm is being kicked out of the cell into the bloodstream. Turns out the synthesis of the proteins that are responsible for catabolism, the breakdown of lipids, these are known as the PPAR family. PPAR. Transcription factors that affect. So whereas we don't have operons, turns out you have the genes for all this stuff spread across all 23 chromosomes. Well, these receptors activate transcription factors, which then go and bind at the promoter regions, preceding all of these different genes across all your chromosomes. PPAR alpha stimulates the synthesis of enzymes required in beta oxidation. So you have an increased demand for energy. PPAR alpha gets stimulated. That means you're going to need energy, so you start breaking down all the fatty acids possible. You have medium chain acyl-CoA dehydrogenase. This is what breaks down the things that are 4 to 14 carbons in length. There's 2 mutant MCAD alleles that we know of that we've studied. They can't oxidize fatty acids that are 6 to 12 carbons in length. For some reason, this just does not work. I can't remember if it's the fatty acids that start off in this or even the much longer ones once they get down to be about 12 in length, it doesn't work. I'd have to go back and look at that. Read up in the literature. But anyways, these people suffer from what is known as fatty liver. High blood levels of octonic acid. That's 8 carbon length fatty acids. The fatty liver, the high blood levels of this lead to coma, death for these individuals under certain circumstances. There are numerous diseases, numerous genetic abnormalities that are attributed to mis-oxidation, mis-fatty acid metabolism, loss of the long-chain beta-hydroxylacyl-CoA dehydrogenase, the activity of TFP. These people will not be able to go through and oxidize fatty acids, so they're completely lost the ability doubly from fatty acid oxidation. When you go and you look at the other organelles that are going to be in eukaryotes, you have what are referred to as the peroxisomes. These are organelles found in plants and animals. The peroxisomes, their job is some of the similar reactions that you're going to see in a mitochondria, except notice there's no respiratory chain here. There's no electron transport chain, and there is no ATP synthase. What happens in the peroxisomes is that these long-chain fatty acids will be broken down into acetyl-CoA, which is then transported out of the peroxisome and then transported into a mitochondria. Why have a peroxisome and not a mitochondria at all? Because in the peroxisome there's going to be other metabolic reactions and metabolites and products that are stored away from the cytoplasm. It's better just store them away in this one place for later use than have them free floating in the cytoplasm. The glyoxosome, this is the breakdown and then rebuilding of sugars and things like that, and this is going to be more plant only, not animal. Beta oxidation in the peroxisomes, dehydrogenation, pull off some excited electrons, pass those on to FAD. Addition of water to result in the double bond, boom. Oxidation to a ketone. And then thiolytic cleavage by coenzyme A. So you go through, add in the water, get the double, the hydroxyl, strip off the, get your carbonyl, and then split off. You now have an acetyl-CoA, and you now have coenzyme A attached to the new carboxyl terminal end. The differences in the peroxisome, some minor differences in the enzymes, flavoprotein, acyl-CoA oxidase. This induces that double bond. Okay, this is going to be peroxisome only, not the mitochondrial version. The enzyme then uses catalase to cleave hydrogen peroxide to water and oxygen, so that you now have hydrogens that can then, the water that can then be used to insert in to give you the hydroxyl, which will then become the carbonyl bond. Turns out the peroximal systems, the peroxisomes, are really good at long chain fatty acids or branch chain. The mitochondria can't handle the extremely long chains very well. Transporting them in gets to be a bit difficult. And the branch chains, it just does not have the enzyme responsible for taking care of those. Defects in the peroximal oxidation. I'm really not going to sit here and spend much time on these. Zellweger syndrome, inability to make them. They're just going to lack the metabolic activities. They can't break down, certain long-chain fatty acids. X-linked, we're just going to call it XALD, X-A-L-D. Inability of the peroxisome to oxidize very long-chain fatty acids, very similar to Zellweger. No transporter. Here they lack any and all of the products or metabolic activities associated with a peroxisome. We see there's a long-chain fatty acids with methyl branches. This is known as Phytanic acid. This is derived from chlorophyll. That methyl group on the beta carbon interferes with the enzymes responsible for beta oxidation. So you look here, you see up here, this will be where the methyl groups are. So ATP, coenzyme A, boom, here's our carboxy terminus. We're going to do here what's referred to as alpha oxidation. Okay, beta you cut between 2 and 3. Here with alpha, we're going to be cutting sooner. You're going to cut alpha, you get the formal CoA, which becomes formic acid once the coenzyme A portion is removed, which will result in carbon dioxide. Going to go through, you now have prostanol, you got phytanic acid, you're now at prostanol because you're one less. You're going to go through and dehydrogenase, and then you're going to start cutting. You're going to remove methyls there, hydrogens there. Now get a carbon, carbon, carbon. You can remove acetyl group, and then you're just going to keep going and doing this over and over.